I'm going to finish the accounting section up with some examples, but let's take a look at a problem to show you how similar a problem could look here. Suppose a senior class at a small high school consists of 40 students. And then I'm going to ask a couple of questions here. So the first question I'm going to ask is, how many ways could we assign the positions of president, vice president, secretary, and treasurer? Okay, well, repetition is not allowed because we will not assign the same person to two positions. And now let's select 4 students. Let's say A, B, C, and D are 4 of the students, and rearrange them any way we want to, C, B, A, D. Selection A, B, C, D could mean that A is president, B is vice president, C is secretary, D is treasurer, but C, B, A, D would mean that C is president, B is vice president, A is secretary, and D is treasurer. So that would be a different assignment. So that tells me that order is relevant. So therefore, this would be a permutation problem, 40 students, total of 40 students, P4, and that would give me over 2 million possibilities using the calculator. Now, if I ask the question differently, I might say, how many ways could we select a group of 4 to serve on the senior trip committee? Okay, well, this example, again, repetition would not be allowed, but now if we selected 4 students, A, B, C, and D, or C, B, A, and D, they are the same committee. So in that case, we would use the combination formulas, and we would do 40C4, which gives us a little over 91,000 combinations. So now let's look at a mix of some problems here. Number 1 says, suppose we have to select 5 managers from a list of 10. How many ways can this be done? Okay, so here repetition is not allowed because we're not going to select the same manager twice. And since A, B, C, D, E and A, C, B, E, D would represent the same set of managers, then order is not relevant. So this would be a combination problem, 10C5. Now, but in the second example, I'm going to select a manager, assistant manager, and night manager. So in this case, I'm assigning them to different positions from 10 people. How many ways can this be done? Well, A, B, C would imply A is the manager, B is the assistant manager, C is the night manager, whereas CAB would imply a different assignment. So in this case, order is relevant. So I would do this with 10P3. Since there's 3 positions I'm assigning, it would be 3. Number 3 says, how many ways can a 3-card hand be selected from a 52-card deck? Well, there's no repetition because the same person cannot get the 3 of clubs twice. So let's pick 3 cards, like the 3 of clubs, 9 of diamonds, and 8 of spades. Well, that would be the same hand as the 3 of clubs, the 8 of spades, 9 of diamonds. So order is not relevant, so therefore it would be a combination problem, 52 choose 3. Now again, on these calculations, you can do these with a calculator if you want to get the final answer. In this example, 3 cards are selected randomly and given to 3 players. How many possibilities exist? Well, since I'm given a card, one of the cards to each player, then that forces the order to matter. Because if I do 3 of clubs, 9 of diamonds, 8 of spades, that's going to assign the cards to the 3 players in one order. But if I do 3 of clubs, 8 of spades, 9 of diamonds, that's going to assign the cards in a different order. So that forces this to be a permutation problem because the order is now relevant. Number 5 says a card is selected from a standard deck of cards, then put back. The deck is reshuffled. This is done 3 times. How many 3-card hands can you receive? Well, in this example, repetition is possible because basically you're selecting a card, recording it, and then putting it back in and shuffle again. So you can get the same card again. So you could get the ace of hearts all 3 times. Therefore, we cannot use the permutation nor combination formula. You have to resort to the multiplication principle. So there's 52 choices for the first card, 52 choices for the second card, and 52 choices for the third card. So the number of possibilities would be 52 to the third power. Number 6, at a Fiat dealership, a total of 3 cars of a particular model must be transported to another dealership. If there are 25 cars of this type, how many choices are available for transport? In other words, how many 3-car subsets are there? Well, if you chose car 1, car 15, and car 20, it doesn't matter what order you choose them, it's the same set of 3 cars. So this would be a combination problem. 25, choose 3, or 25C3. Now, if we force the order of the cars to matter, like I did in number 7, I'm asking you not how many ways I can choose 3 cars, but how many ways I can load these 3 cars onto the truck. Well, then if I choose car 1, car 15, and car 20, that would imply car 1 goes on first, car 15 goes on second, car 20 goes on third. But if I change the order, then that changed the order which they're loaded. So that tells me that order is relevant. So this would be now a permutation problem, 25P3. And then number 8, at a Fiat dealership, there are 25 cars of a certain model. 15 have automatic transmission, 12 have leather seats, 10 cars have both automatic transmission and leather seats. How many have either automatic transmission or leather seats? So how many have one or the other? Well, here I'm looking for, this is an addition principle problem, because I've got 2 sets. Sets A, we can say set A is the group that have automatic transmission. Set B is the group that has leather seats. And then so I want the number that's in A or B, so that would be A union B. And remember, the addition principle says the number in A union B is the number in A plus the number in B minus the number in the intersection. Well, we know there's a total of 15 cars that have automatic transmission, there's 12 cars that have leather seats, and there's 10 cars that have both. So add these together, then subtract 10, and you get 17. Now, how many have neither automatic transmission nor leather seats? Well, since we know these 17 have one or the other, then just take the 17 away from the total number of cars, 25, and so that would give me a total of 8 cars that have neither. Number 9 says Social Security numbers consist of 9 digits, 0 to 9. If there are no restrictions, how many different Social Security numbers are possible? Well, since there's 10 ways to choose each digit, there would be 10 times 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 10, or 10 to the 9th power, which would be 1 billion. Okay, now, I'm not saying that you could use all those numbers, but that's the total number of possibilities available. Number 10 says, suppose license plate in one state have 4 letters followed by 2 digits. How many license plates can be created if there are no restrictions? Well, if there are no restrictions for part A, let's see. Okay, here's part A. So if there's no restrictions, then in order to do the 4 letters, then repetition would be allowed for the letters. So you would have 26 times 26 times 26 times 26 ways to do the 4 letters. And there's also no restrictions on the 2 digits. So you would have 10 times 10, or 100 ways to do the 2 digits. And so that would be operation 1 would be the letters, operation 2 would be the digits. And then you just multiply those together to get the total. So the total would be 45,697,600 possibilities. Part B says, what if only letters cannot be repeated? So letters cannot be repeated, so that means that the digits can be repeated. So if the letters cannot be repeated, then for the letters, I would have 26 times 25 times 24 times 23, which gives me 358,800. And then, since the digits can be repeated, I can still use the 100 that I used up here. So I multiply that by 100, and I get 35,880,000. And then C says, what if only digits cannot be repeated? Well, if the digits cannot be repeated, then the letters can be repeated. So for operation 1 for the letters, I go ahead and use what I had up here, 456, 976. And since the digits cannot be repeated, then there would be 10 ways to choose the first digit, 9 ways to choose the second digit, which is 90. And then multiply those two together, and you get 41,127,840. This one says a shipment of 20 disk drives were received by a computer store. 4 of the drives are defective, and a sample of 2 are selected randomly. How many samples can be selected? Well, the answer to this would be, out of the 20 drives, how many samples of 2 can you select? And the order doesn't matter, so it would be 20 choose 2, which is 190. Now B says how many of the samples contain 2 defective drives? Well, to get 2 defective drives, you can only get those if you choose from the 4 defective. So here you just say, out of the 4 defective drives, how many ways can I choose 2? And so 4 choose 2 would give you 6. And then C says, suppose one of the drives is tested and one is sold. How many ways can this be done? Well, now that you're assigning the drives to positions, it forces the order to matter. So it's really just like part A, except now the order matters. So this would be a permutation problem, 20p2. Number 12 says, suppose a 5-card hand is selected from a standard deck of cards. How many ways can the following be done? Select 3 kings and 2 aces. Well, to select 3 kings and 2 aces, that means you have to do 2 operations. Operation 1 is you must, out of the 4 kings, you have to select 3. So that would be 4 choose 3. That's the number of ways that you can get 3 kings out of 4. And then out of the 4 aces, you got to choose 2. So the second operation would be, out of the 4 aces, choose 2. So 4c2. And then you multiply the 2 numbers together to get the total of 24 possibilities. The next one says exactly 3 4s. Well, operation 1 here would be choosing 3 4s out of the 4 4s. And then operation 2, since it's a 5-card hand, would mean that you're going to choose 2 cards that aren't 4s, and then you're going to choose from the 48 cards that are not 4s. So you have 4 cards, choose 3, times 48, choose 2, and you multiply those together, and you get 4,512. Now this next one's a little tricky. It says at least 4 hearts. Now in this example, we must find the number of hands that have exactly 4 hearts, and add the answer to the number of hands that have exactly 5 hearts. So to get exactly 4 hearts, then out of the 13 hearts you would choose 4, and then you multiply that by the 39 other cards that could be chosen. So out of the 39 other cards, in other words, the 39 cards that are not hearts, choose 1. And that would be, multiply those together, and you get 27,885. And then for 5 hearts, out of the 13 hearts, choose 5, and out of the 39 other cards, choose none. And that gives me 1287 for the total number of ways to get exactly 5 hearts. And then you just add these two together, and that'll give you the number of ways to get at least 4 hearts. This next one, we have 3 sales forces in our company, A, B, and C. We have 8 members in Group A, 7 members in Group B, and 5 members in Group C. And you must assign a salesperson and alternate from each group. How many ways can this be done? So this would be a permutation since we're assigning them to positions, but you've got 3 operations. So you've got 8p2 ways to assign Group B, 7p2 ways to assign Group B, and 5p2 ways to assign Group C, and you multiply those 3 together. I'll leave 14 for you to read, but let me quickly talk about 15. A lottery consists of 54 numbers, and you have to choose 6 without repetition. So the number of ways this can be done would simply be 54, choose 6, which is 25,827,165. And if repetition was allowed, it would be a much larger number. So that's all I have for this section, and I'll move on to probability.